Hello. Oh, that's loud. All right. So today I'm going to be talking about this tool that I built together with Leo and Hengchu, and it's called StrictCheck. It's a random testing tool to keep your laziness in check. So in the previous talk, Simon was talking about how build systems hopefully do as little work as possible. And I'd like my programming languages to do the same thing, and I think Simon would probably agree. So I want to be lazy, and for a lot of reasons, because I can use infinite data structures, because I can easily memorize computations, because I get certain kinds of compositional performance guarantees, but I don't want to belabor these points because I think a lot of you might agree with me. Instead, I want to talk about why laziness can be sometimes hard. A lot of the time when I bring up laziness to some people who are less convinced about the stuff on the previous slide, people say, oh, well, but laziness is hard to reason about. And I agree. And when I say that something is hard to reason about, I'm describing my relationship with my craft as a programmer. I'm not just describing the thing, I'm describing how I experience that thing. When I say that something is hard to reason about, I mean I can get confused about what that thing means, and I can't clarify that confusion automatically. So I think laziness is hard to reason about. But instead of reasoning directly about laziness, I want to talk about strictness instead. Because after all, when we say how lazy a function is, we're talking about how much it doesn't do. And when we talk about strictness, we're describing how much a function does do. So how much do these two functions do? They look really similar, right? In fact, they've only got two lines interchanged in each other. They're both functions that take some number of elements off of a list. They both return the empty list when given an empty list or the number 0 as input, and they both recurse in any other case. So they would seem to be basically the same function, except for these two different lines in different order. So, let's look at number 1. Gonna make a big number, and I'm gonna make a list that's ultimately the empty list, except for it takes a lot of work to actually compute this list, because I want to show that something goes a little bit strange. So if I take 0 from this ultimately empty list, then I end up waiting, and waiting, I'm actually still waiting. Because the empty list takes a long time to compute, and because the first pattern match in this function matches on the empty list, well, I'm stuck. So what about the other one? Well, this one works when I give it this really, really heavy, expensive empty list. But say I make a really expensive 0, and I take 0 from that empty list. Well, once again, I don't know what to do. And these functions are differently strict. One isn't stricter than the other. One is really strict in one argument, one is really strict in the other. They evaluate in different orders and to different degrees. And I find this confusing. It wasn't immediately obvious to me when I stared at that code right off the bat which one would do what. And I want to clarify my confusion automatically. And one of my favorite tools for clarifying my confusion is QuickCheck. But strictness is kind of hard to capture. And in order to capture something, we need to capture something. In order to do property-based random testing, like QuickCheck allows us to do, we need to be able to describe what it is that we mean to test. We need to be able to write specifications. And then we need to be able to test those specifications in order to actually find out whether our properties hold. So to randomly test for whether functions are strict, we first need to know, what does it mean to be strict? What is strictness? So my intuitive idea about strictness, when I think, oh, how strict is this function? What I think, first, is how much does this function evaluate its inputs? And that's to say, how does it behave when its inputs are undefined? This turns out to be an equivalent way of phrasing the same question, because if a function evaluates an input in order to produce its result, then if you feed it undefined for that input, then it's going to explode. So a little bit of an easier way of thinking about how strict a function is thinking about what happens when you feed it an input that's going to be exceptional. So let's look at the humble function plus. Well, if I add 1 and 2, then the answer you all know. If I add undefined and 2, and notice this is defined over machine integers, so no funny business about lazy gnats. Well, I get an exception. If I add 1 and undefined, then I get an exception. So I'd say plus is 100% strict. Plus does exactly all the work. And this way of thinking, by the way, is called forward strictness analysis, and it's really cool, and there are some people in the audience who have some really cool work about it that you can look up. Now, let's take this function f instead. F takes anything, any number, x, and returns 42, without really doing anything to x. So if I call f on 1, I get 42. If I call f on this very large number that takes a while to compute, I get 42. If I call f on undefined, it doesn't explode, we just get 42, because nothing had to happen. So f is 0% strict in its argument. Now what about this function, safediv? Well, safediv, it checks, like we don't want to divide by 0. So safediv checks to see if the denominator is 0 before it actually performs any division. So depending on whether y equals 0, we're either going to return nothing if y is, or we're going to return just the quotient if y isn't 0. Well, what happens depends on the context in which we evaluate the result. Because if I force all of the result to be evaluated and y wasn't 0, well, then that means that I'm going to have to force both x and y to be evaluated, because I'm going to get this just the division, and I need to evaluate everything. But if I only force the outermost constructor, then I don't actually need to divide x by anything, and x can remain unevaluated. So this is also called projection-based strictness analysis, and there's some really cool work about that probably there are some people in the audience you could talk to about that as well. So I have my function, safediv, and I have some contexts that I might evaluate safediv in. So when I call safediv in a particular context, I'm curious about how much does that outer context, how much does that setting of safediv actually evaluate? So if I print safediv applied to undefined and 2, that's to say if I safely divide undefined by 2, and I print the entire result, that's going to force the entire result to be evaluated, that whole maybe A. And what that means is that the undefined, the x, is going to have to be forced because we actually divided x by y, and that blows up. On the other hand, if I just ask whether the result was just or nothing, I can say that definitively without actually performing any division whatsoever. So to get a little bit more formal, I want to say that a context, when it's applied to a value, demands some portion of that value. When I say demand, I mean some subpart of that value. You may have noticed I'm using some colors that I've made a custom syntax highlighting for the stuff that I've been doing so far. And that's very deliberate. So pay attention that blue is contexts, and yellow is values, and red is demands. And for those of you who are colorblind, I've done my best to make it possible to distinguish things by context and not just by color. So if I print just 5, then that requires the entire value to be evaluated. If I just ask whether it's just, then I just have to evaluate, I merely have to evaluate the outermost constructor. And if I apply the constant function returning 2 to just 5, well, I don't have to evaluate anything. And I can represent these kind of partial values, these prefixes of values, using a Haskell data structure that I'm going to call eval. So eval is either E of A, standing for evaluated, because I can't fit things on slides if I type out the words evaluated, or U, standing for unevaluated. So to represent the demand on some type like maybe int, I can say, well, either the outermost maybe constructor was evaluated or not, and then if it was a just, then there might be an integer inside that was evaluated, or maybe I didn't evaluate that integer at all. So now we can use this to write down a strictness specification for safediv. That's to say that a strictness specification is a function on demands and values, because I want to say, how strict is this thing supposed to be? If I demand some amount from its result, and given the particular inputs that it was given, what does it actually need to evaluate of its inputs? So a specification in general is a function from the demand on the context's, the outer context's demand on the result of a function and the input values to that function to the predicted demands on the inputs of the function. So let's, write a specification. If there's no demand on the output if there's no demand on the output of safediv, then I couldn't possibly demand anything of the inputs because that would be ludicrous. If I demand just the outermost constructor of the result of safediv, and that outermost constructor happens to be nothing, then I always evaluated y, because I had to check whether it was 0 to produce that nothing, but I didn't evaluate x. If, on the other hand, I happen to demand the outermost constructor just, then I also evaluated y, but still not x. But if I evaluated the inner integer of the just, then I finally demanded both of them. So then, given one of these specifications, strict check evaluates some function with randomized inputs and contexts. So there's our random testing. And then we need to observe what actually happens when that function runs. And then to tie everything back together, just like with ordinary property-based testing, we need to compare whatever specification, whatever dynamic property we write down to what actually happened during our test run. So for the rest of the talk, I'm going to talk about how we actually managed to make this work. And we make this work by augmenting traditional property testing. That's to say quick check. We literally build on top of quick check to measure strictness and to specify strictness and to tie those pieces together into what will initially look like a little bit of a knot, but hopefully I can untie it for you. So this is what traditional property-based testing looks like. I generate some inputs, I feed them into my function, and I get some result, and then I compute some kind of a property that relates the inputs to the result in some interesting way. And the property succeeds or it fails. It produces a counterexample if it fails. It produces some nice affirming ASCII text if it succeeds. But this isn't quite what we want, because we also care about what context the result is evaluated in. So we're going to randomly generate that. And there's some interesting details about that, which you can read the paper to find more about. And our properties that we care about aren't really properties about inputs and results. They're properties about demands. So let's make some room there, because I'm going to add some more pieces to this graph. So we need to find out what demands actually happened. So we introduce this function, and I'm going to put function in air quotes, that I'm going to call instrument. An instrument takes an A, anything, and maps it to a pair of that same type and a demand on that type. But what's sort of magical about this, and I say sort of magical, is that as we evaluate the A, the demand, this demand data structure that's just a Haskell data structure, gets mutated under the hood. It's actually a pointer-based data structure hidden away from you, so that it reflects the part of the value that was actually evaluated. Now, of course, this is completely referentially non-transparent. It's totally opaque. It's totally unsafe. It uses unsafe perform IO, but it doesn't touch any of the internals of the compiler. It doesn't modify the interpreter. It doesn't do any fancy hocus pocus. It just uses unsafe perform IO in a way that we wrap up on the outside so that everything is pure and lovely and wonderful. So what we get now is that instrument splits our inputs into these instrumented inputs and this magically entangled demands on those inputs, so that we can then observe what passes into the function, what actually gets demanded by the function, as reflected in this like shadow mutable data structure. And then we do the same thing, because we actually need to care about the results that the context induces as well. So now we've spliced in this instrumentation on both sides of the function. Well, now we have what we want, right? Because our specifications were about inputs and demands on inputs and what the demand the context made. So we can say, all right, we've got a specification. We've got our inputs. We've got the demand that the context places on those inputs. So we can predict what demands should be placed on those inputs. And note that, as I said before, the specification is just a function that takes reified Haskell data structures that represent the demands on the data structures in question and computes some pure result. And we can actually compare that to the demands that we observed during execution. And in the end, you wrap all of this up and you tie a nice bow, and it all just goes through. Now, I also want to note that here I've sort of written, oh, well, we're comparing specifications for equality, but sometimes that's not what you want to do. Sometimes you want to compare specifications to say, is this at least as strict as this? Is this no more strict than this? And there's a lot of room for improvement and interesting development left to do, because the thing about this framework that I'm least satisfied with, the thing that I'm really excited to see more work in, is figuring out, now that we can actually test strictness properties, now that we can write down exactly how strict something is and check it randomly, how do we write down specifications that we actually care about? How do we write down specifications that mean what we mean to say and aren't unwieldy to deal with? That being said, it's online, and you can play with it, and you can tell me. And also, you should totally read the paper, because there's a lot that I've left out here. In the paper, we talk about how we observe demand efficiently. There's only a small constant overhead to this kind of instrumentation. We don't evaluate functions multiple times. We can run on compiled code, even optimized code. So you can test the very same function that you use in production with all of your compiler optimizations turned on. And there's no boilerplate necessary for testing there's no boilerplate necessary for testing algebraic data types in Haskell, because we use some pretty interesting generic programming to make all the pieces fit together and get derived automatically. And then in order to instrument things and pull everything through in a random way, we have to generate these random contexts. And to do that, we have to generate not just random functions, which we could already do with quick check, but we have to generate random functions with random strictness. That's to say, oh, the function might start evaluating its inputs, but then it says, oh, all right, I'm done. And it turns out that not only is this necessary to generate random contexts, but it's also, what it also allows us to do is to randomly test higher order functions. So you can say, is my specification of map or fold or something else, is that exactly how strict I expect it to be? We could distinguish between fold L and fold R, for example. And then we worked through an extended case study with this really beautiful data structure designed by Chris Okazaki, his persistent lazy queues. So I invite you to check us out on the internet. I would love if some of you played with this and told me about what uses you find for it, and especially write down some interesting specifications, because I'm really curious to see what you come up with. Thanks.
All right, thanks a lot. Yeah, plenty of questions. So let's start with a general one. Could this strictness analysis be done statically instead of dynamic testing?
That's a really good question. There's a lot of strictness analysis that you can do just statically, but the kind of things that you can't do statically are testing what I would call dependent strictness. That's to say, when how strict a function is depends on the values of its inputs in a non-trivial way. Determining statically exactly what that function evaluates of its inputs is equivalent to the halting problem. So there's never going to be a static specification system that can let you write down exactly what you mean there. So we get a lot farther to being able to express very complicated strictness properties using dynamic testing. That being said, there's a lot you can do with static strictness specification, and there's some really cool work there.
All right, thanks. Imagine you have the function f applied to x equal undefined. And yeah, Jenny Hackett is wondering, is this function strict? What answer your system will give you? And what is the right one?
So the system doesn't look for undefineds. The system doesn't feed undefined inputs into functions, and it doesn't deal with functions that produce undefineds. So I can say right away that the answer the system will result in is that the system will crash. The correct answer, I'm not sure. Let's talk about it. But the way that the system works internally is it doesn't make use of feeding undefineds through things. It uses this mutable pointer structure.
All right. Cool. Another anonymous question is, does the use of unself-perform I/O make it harder to parallelize test cases?
I shouldn't think so. When we instrument a data structure and we create these shadow data structures that mutate pointers under the hood to determine what demands we actually exert, the only place that has a reference to the mutable reference, the only place that actually scopes over it, is buried inside of the instrumented data. So you should be able to parallelize as much as you want. I don't think there should be any threading difficulties.
All right, cool. So yeah, a question of myself. How critical and good needs to be the generation of context in order to trigger the bugs in strictness? And what is your experience with that? How smart you need to be on that part of the strict check?
That's a really great question. We spent a lot of thought in tuning the random generation of contexts. There's actually a full-page appendix in the paper that lists the entire code that we use to generate contexts. And there's no pure theorem that says, oh, this is the correct distribution. But that's usually the case in random testing, is that there's almost like an aesthetic or an empirical perspective that you have to take in trying to tune your distributions. So the one that we picked, it tries to avoid generating functions that overlap in the things that they demand. So a function that takes different input will more likely demand different things. So we try to spread through the space of different interesting strictnesses. But there's definitely room for experimentation there.
All right, thank you very much. Let's thank Kenny again.